Continuing on with class 14, we're going to do another maximum shear stress theory example, and this one is Shigley problem 5.1 part C, at least in one of the editions, where we have 100 megapascals and a 75 megapascals in shear. So the good place to start when doing these is to draw the stress element. So there's 100 megapascals, and the shear. By the way, if you always want the sign convention, you could think of this as being face and direction. So if it's negative, that means either the face or the direction is negative. So let's take a positive face, which is the positive x, and the negative y direction. So that means that shear goes downwards. And you could test that idea out on any of those, and it will come out correctly. So that's the direction that they mean for a sign convention. So for this first one, we're going to use 350 megapascals. First, we need to find the principal stresses. So I want to plot this out right here, and I think I didn't leave a lot of room for myself here. I wish I had made it just a little bit bigger, but I think this will come out fairly close if I'm careful in my Mohr circle, and I just wasn't careful enough. Look at how I just made that line kind of messed up. That's going to be affected. And I think I decided that each block was 10 megapascals, so it's going to go 10, 20, 30, 40, 50, 60. That's not good. Let me do a different one here. Each block, oh no, okay, sorry. So it goes 20, 40, 60, 80, 100 right there. And this is 120 and so forth. So here's 20, 40, 60, 20, 40, 60, 80, 20, 40, 60, 80 right here. So right here, here's 70, so right here is 75, and right here is 70, so right here is 75, and so we have 100, and so this face right here, this is going clockwise, so that's what we usually consider in the upper half when it comes to the shear. So we're going to plot out where 175 meet. Hopefully I did that okay. And right down here, it's going to be right there on the thing because we're plotting out this face. So we will plot this through, and hopefully it comes out somewhere near 50. And it did right there, right? Because the center should be the average of the two normal stresses, which is just going to be 100 divided by 2, or 50. Yes. And then the radius of this, we're going to take this leg right here squared, so that's going to be that 50, and then this distance right here, which is going to be 75, and we do those two and we get 90.14 megapascals. And if we do very careful circles right here, you can kind of, didn't do terrible right there that time. Okay. Here is going to be our sigma A, and here is our sigma B. So we say sigma A is equal to C plus R, or 50 plus 90.14, 140.14. And then you see that it's positive, it's tension. Sigma B is C minus R, or 50 minus 90.14, or a negative, what is that right there? I say that it's a negative 40, yeah, negative 40.1 megapascals. Good enough. And we also know that this is the big Mohr circle, right? There's going to be another one right in there somewhere. I I shouldn't even bother with this, but this I will anyway. So he's going to be in there somewhere. Didn't do a good job of that. And then this is going to be pretty much 1/2 of, so it should be, it's not true, right? No, it should be that. Oh, no, okay, it should be the one, this should be 70, right? So like 70, yeah. Should be the center of this Mohr circle. There you go. There you go, right there. There's our 3 Mohr circles. But the most important one is the big one, because that's where tau abs max comes from. And we recognize that's the same as this radius right here, right? This is the R. So up to there, tau abs max is equal to R, which is equal to 90.14 megapascals. So our safety factor in maximum shear stress theory, it could be this yield strength divided by 2, and the yield strength we were told was 350, divided by the abs max shear, or 350 divided by 2, which should be, what's that, 150 and 25, 175, divided by 90.14. And if we do that, we end up getting 1.94 is our safety factor. But let's go down to here and do our failure loci. See, I remembered to call it that time. And I think I go by 100s by here, every other one. So there's, that right there is 300, here's 350. And there's 100, 200, 300, here's 350. And 100, 200, 300, here's 350. And 100, 200, 300, 350. Nope, one more. 100, 200, 100, 200, 300, 350. I guess that's right. Okay. Didn't look right to me. So there you go. Could have gone up a little higher. Okay. And just double checking this thing. Does it look right? I think it does. Okay. Oh boy, that does that? Yeah, I guess so. Yeah, okay. So we want to plot out our point here, and our points are at 140 and 40. So 140 is, okay, so here's 100 right here, and here's 150, so 140 is like right in there. And then here is 50, so 40 is right there, right? Remember that it's negative, and we're doing A and B. So this plot point should be right in there, I think. Right in there, okay? So we're going to come from the center. You know, our pencil lead thickness, I actually am using a 0.5 this time instead of the 0.9. The pencil I prefer. How'd I do? It's not terrible. All right, so this is O, and this is A, and this is B. So let's use our millimeters here. So that's going to the finest that we have, and kind of make sure we get as close as we can to being correct here. I see that to be, and I got to take a look really close. 1, 2, 3. It looks like 13 millimeters to me. What did I say before? I said it was 14. Oh, wow. Okay, I think I might have been fudging it. One thing that you can do is you can go to this guy right there and check him out. Yeah, so now I'm starting to think it's more like 14. See, there's 1, 2, 3. It's getting close. It's getting close to that 14. I don't know if it's 100% 13, right? This pencil lead thickness matters. So I'm going to cheat because I know this is going to be correct and go OA is going to be 14 millimeters. And now I'll go OB, And so remember that I'm started at the 1 right here, so that's actually 10, 20, so it's going to be 20 something. And looking closely at there, I'll actually go backwards and go 1, 2, 3. It's hard to say that OB right there, I said that it was 27 millimeters. And so the maximum shear stress theory, according to this right here, is going to be OB over OA, remember? All right, so this is the distance to failure, and here's the distance to the actual. So we take 27 and divide it by 14. And I get 1.928, call it 1.93. And this is approximate right there, right? Because I'm using this right here. But I can also, if I want to, go to a AutoCAD, right? And this is my sloppy way of doing things. So excuse me, I like to use offsets for things. So first off, that one's 37.5. That was the other problem I just did previously. Let me go to this one. There's a 3. Here's one where I made it 350. And I'm going to go down and I'm going to go 140.1 is my offset, and that's going to be to the right there. And then I'm going to go offset and I'm going to go 40.14. I think that's going to be correct right there. And I'm going to come down right there. So I have an exam I have to give here in a minute, so we will end soon here. So right there is the center to the thing, and right there is my intersection. But I can extend. I don't know if it'll do. It's doing the automatic extend. Okay, so I can do that right there. All right, so I can get rid of my. Let me get rid of these lines. Whoops, no, I don't want to do that. Dummy. And so let me take my dimension. Here's an aligned dimension, and boom, there's 282.9999999, and then I'll take it to right there. Okay, so if I take and I divide 283, a lot of sig figs there, 145.74, right? And I go 283 and 145.74 and divide it. I get, you guessed it, 194, 1.94. Wee! So it was all about my pencil lead right here that, and I kind of fudged because it could have been more like 13 here. This could have been more like 28. Would have given me a bigger number, I think closer to 2, right? But we could see that we have confirmation of the failure loci. So I will do my last video after I give this exam. But that was example 2. I'll do example 3 in the next